Okay, for this problem we have a loop of wire. Let's see. That's like that. And we have a magnetic field directed perpendicular to the plane of the coil. So that means that the magnetic field is directed like this. And so what this is talking about is it's talking about something called flux and magnetic flux. So magnetic flux phi B is equal to the magnetic field B times A, the area of the wire. So when my loop is perpendicular to the B field, that means that there's a lot of flux going through it. If my loop was not perpendicular to the B field, so if I had, like, my loop was like this in the page, but my B field was also pointing into the page like this, then there's no flux here. So no flux, because there's no B field going through the area of my loop. Here there is, because my loop, the face of my loop, the B field is going through it. Here there's no flux, there's no B field going through the face. In order for it to go through the face, the B field would have to point into the page or out of the page. Okay, so we are calculating the EMF induced in the coil. So the EMF is just the voltage induced in the coil. And I like to think about it is in order to have current running through a wire, then I need to have a changing flux. So there's a couple of ways that you can have a changing flux. One is that I can increase so in this case I can increase or decrease my B field. If I increase or decrease my B field, that means let's say I increase it, that means I'm going to have more field lines going through this area. And so that means my flux will be changing, right? My B will be increasing right here. So if my B is increasing, then this is changing, and that induces a current in this wire. The other way that I can change flux is I can change the area. So I can either change the B field or change the area. So how can I change the area? I can make my loop smaller, or I can rotate my loop. So imagine if my loop is like this, there's no flux, right? There's no B field going through it. But if I were to rotate it from this position to this position, then the flux is going to be increasing, because the area of my loop that has flux going through it, when I go from this position to this position, the area is increasing because I'm rotating it into the B field. So those are the ways that you can increase the flux. So in this case, the way we're increasing the flux is that it says that the area of the coil is increasing at this rate. So here in this example, we're increasing the area. So my formula for EMF is EMF of the coil is equal to, all right, so let's back up. EMF, the name is wrong. It stands for electromotive force, but it really isn't a force, it's voltage. So if I induce a current in this wire, in order to have current, I have to have a voltage difference. So what I'm looking at is, if I were to hook this loop up, let's say I had something like this, and I were to hook this loop up to, say, an ammeter, right? I'm going to measure current, and I'm also going to measure a voltage. So there has to be a voltage difference across this loop in order for current to flow. So that's what this EMF is. It's actually a voltage. So I have EMF is equal to a negative d phi dt. And so what this negative means is, it just means that it's opposite. So if the flux here is increasing, then the direction of the current is going to be to oppose this increase. So what that means is if I have more of a B field going through this loop, then current is going to flow to oppose that change. It doesn't want to have more flux going through it. So it's going to induce a current that's going to oppose that, or subtract off some of my B field. So that's what this negative is. So I'm not really going to worry about it in my numbers. I just want it to say, hey, my EMF, the current moves in such a direction to oppose that increase or to oppose that decrease. All right, so now I'm going to say d dt of the flux is B times A. And now in this example, my B is a constant, only my A is changing. So that means I'm going to have a negative let's see, I'll erase that. Negative B, because that's constant, and then I'm going to have dA dt. And so they tell me that the area is increasing at a rate of 5 times 10 to the minus 3 meters squared per second. So I'm going to rewrite this. E is equal to, and again, for now, I'm just going to do the magnitude, so I'm not going to worry about that negative sign. And so my B is going to be 0.3 Tesla times, and now this is my rate of change of area, so 5 times 10 to the minus 3 meters squared per second. And there's a lot of different, for Tesla, there's a lot of different units, but let's just look at the units. Well, let's finish this first. So E is going to equal 0.3 times 5 is 1.5, so 1.5 times 10 to the minus 3 Tesla times meter squared per second. And now, so let's just do units here. We're going to have a Tesla is equal to a volt times seconds over meters. And here, so that's what my Tesla is. And now if I'm going to multiply it by this meter squared per second, so times meter squared per second. So that's my Tesla right here. That's my T. And then times meter squared per second. I cancel the meter squared out, I cancel the seconds out, and I'm left with volts, just as I thought. So, and now 1.5 times 10 to the minus 3 is 1.5 millivolts. So millivolts. 1.5 times 10 to the minus 3 is milli, and my units are volts, so I get 1.5 millivolts. All right, let's go to the second